You guys are working on a homework that's due on Friday. Make sure you upload it before class time. What the deadline is 12:20, right? Make sure you get it uploaded. And then we're going to do a quiz. We'll be in Wallace Hall 123 on Friday, so we'll do the quiz in there. The quiz will be about 15 minutes, and it'll be at the beginning of class. So make sure you show up in class on time. Yeah. It'll be over what you did on the, mainly over what you did on the homework and the reading in chapter 1. A heads up, the way I work the quizzes and the homework is that I'll assign the homework and I will typically put a due date on it of the day before the quiz. So let's say that this homework was something we needed to check before you did it. I would assign it. The due date would be next Wednesday, which means in class we will go over the homework. You will check your answers, and then you have 2 days before the quiz then to go back and correct if you got something wrong. Fix up your homework, get it right, upload it. And then the quiz will be mainly over the homework that we just did. So the intent here is that you give a good try at doing the homework. If you get stuck, then we can figure that out and help you get unstuck, and then you fix up your homework and then turn it in correct. The quiz will cover that material. So if you tend to get into a mode where you don't do the homework by the day that we go over it in class and you expect to then try to figure it out between there and the quiz, typically you won't be successful. You need to do the homework on your own, by yourself. Give it a shot. When we go over it, it's not intended for you to try to rapidly copy down what I show you, because you can't. I go too fast. But it's intended so that you can fix up what you didn't understand or you got wrong. And then you learn it, and then you're good on the quiz. So if you do that, you will do good on the quizzes, if you can do the homework and follow along in the reading. Okay, so this particular time, since it's just writing short answers and you can look up the answers on the internet, I'm going to collect that on Friday right before the quiz, or actually after the quiz. No, I'm sorry, you're uploading it. Sorry, new protocol. I usually collect it after you guys do the quiz. But you're uploading it before the quiz, and then we do the quiz, and I'll grade both of those. Make sense? Okay. Should go okay. Yeah, I think that's all we need to talk about. So look for another homework that will be assigned by Friday or before Friday that you'll be working on over the next week. All right, so today we're talking about chapter 2. So you should start reading chapter 2 in your book. And this has to do with pressure, temperature, and density, which are key elements of fluids. You guys have seen these before in physics and chemistry, right? Let me just check my video stream here. Yeah, okay. So the idea is that we have air molecules. Since airplanes fly through air or some other kind of gas, and if you have a surface, maybe you just hold your hand out the window of the car, you feel those air molecules hitting your hand, right? If we have a piece of paper and we hold it here, you feel the air molecules hitting the piece of paper. And the force depends upon the area. Obviously, the more area, the more molecules hit. And so we don't typically, with fluid flow, talk about the force, because every time we change the area, we'd have to recalculate the force. Instead, we talk about pressure, which you've seen before, which is force per unit area. So then, if you know the pressure and you know whatever size your area is, whether it's a big 4x8 sheet of plywood or a little piece of paper, then you can calculate how much force it has. So that's a property of the fluid, a property of the air. And typical units, metric is force per unit area, newtons per meter squared, or pounds force, usually use PSI. And often we'll refer to, let's say we pick a point B on that area, we'll talk about the pressure at the point B. But if you're a mathematician, you go, well, a point has no area, so how can you talk about force per unit area if we have no area? And so really, it's a fictitious concept, and just like a lot of other mathematical concepts, we'll define a small area dA, and then we'll take the force on that area. So we have the force acting on that little area, and then we take the limit as that area goes to 0. And that will be what we call the force at that point. So really, if you think force at a point, just think of a really tiny area there, and the force is averaged over it. And that's how you can get a pressure at a point. All right, so far so good? So another property of the fluid is density. And if we put the air molecules in a container, say a jar, and this jar has a certain volume, then we want to know, well, how much molecules, how much air is in that volume? So we could count all the molecules and multiply by the molecular weight and get a calculation of the amount of mass in there. But the flow or the fluid quantity that we use to define that, again, is not dependent upon the volume of that thing. And so we're going to measure what's mass per unit volume. So if we had a volume, we weigh the mass, divide by the volume, and we get density. Again, you know that before. You've seen it in chemistry and physics. But we're just defining everything in chapter 2 carefully. And so density is rho. It's mass per unit volume. And I probably said this before. You guys that are sitting over there, if I start writing too small, say something immediately. I'll do my best to make it bigger. I guess you could start bringing binoculars, and that would be a clue to me. If you pull your binoculars out, then I should start writing bigger, huh? So units on this, metric is kilograms per meter to the third. Pound mass per foot to the third. Or slugs per foot to the third. And in this class, we tend to not use pound mass because slugs is a consistent set of units. We'll talk about that in a couple days, if not next time. And we'll talk about how if in some of the problems in the book, they will give you pound mass and you need to make sure you convert it to slugs. And you've talked about that in chemistry and physics as well, right? So in this class, we will stick to kilograms and slugs for the English units. Often, you'll get data with pound mass because that's one of the things people talk about. And then a density at a point, same deal. You take a little mass contained into a little volume. So you would put a little volume inside here, shrink that volume down, in the limit, and that's the density at a point, even though we know at a point which has no physical dimensions, there's no way an air molecule could fit in there because it has 0 volume. So again, it's a mathematical fiction. All right, so pressure is the force of the molecules hitting a surface because the molecules are moving around. Density is how many molecules mass per unit volume. So far, so good, right? And then one of the last properties of a flow or a fluid that we need to talk about is temperature. So one of the things I said, if I start writing too small, you need to say something. If I start erasing something and you haven't copied it down, raise your hand and say, hey, hang on a second. I have no problem with waiting. All right, so temperature. What does that mean? It's hot or cold out, and we sense that with our skin. And what we're really sensing is the average kinetic energy of the molecules. And we sense that because if the molecules have a high kinetic energy, they're hitting the surface faster and harder, and they transfer that energy to your skin, and that's what you feel as temperature. And that's where you get heat transfer. All right, so it's a measure of the average, the right average in here. Because you don't track each little molecule. There's so many molecules, there's no way you could track them all. And the units that we look at for this are the usual ones, you know, degrees K, degrees C. So centigrade and Fahrenheit are not absolute temperatures, whereas Kelvin and degrees Rankine are. They're relative to what's called absolute zero, where there's almost no kinetic energy or no motion. And in fact, if you know the temperature, you can calculate the energy using Boltzmann's constant. I need a Z there. We won't be doing this, but if you ever want to impress your friends, you can memorize Boltzmann's constant. Or maybe convince them that you're a little nerdy. I don't know. Yeah. Yes, and in this, T has to be, in fact, this is in degrees K here. So if you use this number, then temperature has to be in degrees K, so the units cancel and you get joules. So high temperature means fast movement, low temperature means slow movement. All right, so temperature, density, pressure. Those are quantities that we care about. Pressure is really important when we start talking about aerodynamics, because if we have a wing and we want to know, well, can we generate lift to keep an airplane in the air? We want to calculate the pressure all around the airfoil or the wing so that we can find out if there's higher pressure on the bottom and lower pressure on the top, and we get net force upward. All right, so think about the definition of pressure. It's the force on an area. Density, it's how much mass per unit volume. Kinetic energy is temperature. And now let's do a thought experiment on a bunch of molecules in a box. And I guess if we ordered our molecules from Amazon, it would have the little, is that the symbol for Amazon on it? Because it just came delivered by UPS, right? Anyway, so our box has, that's a joke, by the way, molecules in it. And on this face here, we'll define an area A on that face there. And then we can measure the force on that area of the molecules from the inside. So draw an arrow this way. That's the force acting on that area. And then this box has a volume V. And so we can obviously calculate the density of the molecules because we take the mass, total mass in the box, divide by the volume, we get the density. Okay, so we're good. We could, in fact, weigh the box filled with a vacuum. That might be kind of hard because the box would collapse. But you know the weight of the box, put the air in it, weigh it again, you calculate the mass, divide by the volume. So we get that. We measure that force on that area. And we can calculate the pressure. And then we measure the temperature with a calibrated thermometer. So that's the kinetic energy. All right, so here's our thought experiment. Number one, the volume is fixed. And the temperature is fixed. It means it stays the same, so we don't change either of those. What happens if we let the density go up? What happens to the pressure? So there's the box, same temperature. So the average velocity of the molecules is the same, but we add more. What would you expect to happen to the pressure? It's got to go up, right? Because there's more molecules hitting per unit time. And so that's true. The pressure will go up because there's more molecules. Okay, so got that. How about, let's do a different scenario. So thought experiment number 2, volume is fixed, density is fixed, so it's the same number of molecules in the same box, but the temperature goes up, which means the kinetic energy goes up. So now the molecules are going faster. What happens to the pressure? It's going to go up, right? Because now the same number of molecules are hitting, but they're going faster, so there's more energy transferred. So the pressure is going to go up. And where I'm heading with this is something I'm sure you've already seen. It's called the ideal gas equation, or the equation of state for gas. So this thing is sometimes called the ideal gas law. For 10 points extra credit, could you write it down right now? Do you remember it from chemistry? Or maybe you read the book and read ahead for today. The way we use it is that the pressure is related to the density and the temperature by a constant R that depends on what gas we're using. So we'll use it as P equals rho RT. And R in this case is called the specific gas constant. in chemistry, I think you use a form of this that uses the ideal or the universal gas constant, but then you've got to multiply that by another term, and gosh, I've forgotten what it is. You remember what that form is? It uses little r. Maybe you multiply by the molecular weight or something like that. Well, anyway, we're not in chemistry. So it says, if the density goes up, the pressure goes up. If the temperature goes up, the pressure goes up. So we kind of sort of derived that, didn't we, when we were with our thought experiments. And this R thing is the specific gas constant. And it changes depending on what the gas is. If you have air, it's one value. If you have helium, it's another value. But for air, I'm going to give you the numbers. These are in your book. And we talk about air a lot in this class because our airplanes fly in the Earth's atmosphere. If we're designing a Mars airplane, we'd have to use a different number, which is becoming more and more probable, right? There's a lot of missions. In fact, a bunch of missions launched toward Mars just recently. Do you remember why? Or are you keeping track of that? It's because the Mars and the Earth are on the same side of the sun during this time window, and if we launch now, it's the fastest trajectory to Mars to get there. Anybody in here want to go to Mars? You do? Cool. So if you do, you have to promise to Zoom me from Mars and say hi. Although there's a couple minute lag time, I think. That'd be cool. I guess you've seen that movie, The Martian? Yeah, that's cool. All right, so air. So there's the metric version. Here's the English version. And these are in your book. These are on page 71 in the 7th edition. And on page 65 in the 8th edition. Anybody using the 6th edition? Does everybody have the 8th edition in here? Just out of curiosity. You have the 8th? Anybody have the 7th? Got a used book? Okay. By the way, this book is very good. The guy that wrote it is famous for writing this series of books and is a great communicator. I saw him lecture at a conference 10 years ago, and he's just a really cool guy to listen to and talk to. He communicates really well. So the book is very well written. I encourage you to read it. All right, can I erase this? We're good? And normally I'd be using this as well, but then I've got to move the camera. Are we okay with the way this is going? Sometimes I will expand over here because we'll have long equations. All right, here's an example. We're on the Earth. We have air at sea level. And we'll talk more about this, but it's at what's called standard atmosphere. Which is a standard set of tables that somebody developed a long time ago so we could all be on the same, literally the same page when we're talking about sea level. And so in this standard definition of the atmosphere at sea level, so the height is 0 meters. And the temperature (288.16 degrees K). That's something you and I could easily measure, right? Grab a thermometer, go to the spot and measure it. And pressure is easy to measure. You buy a pressure transducer, which are just little chips that are cheap. You can buy one built into a device. You can probably get it on Amazon for 25 bucks. We can measure the pressure. So we measure the pressure there, but density is hard to measure because you have to collect a small volume and then weigh it somehow, and you have to have that volume and everything. So we're going to calculate this based on the ideal gas law. So you guys do that. The R value that we need is in metric, yeah. By the way, just for the heck of it, is this cold or hot? Does anybody know? Anybody watch weather forecast in degrees Kelvin? Hardly ever, right? Is it hot? So what we need to do is convert it to degrees centigrade, right? So in degrees centigrade, it's 15.16 degrees centigrade. At this point, there's usually a few people in the class that grew up in a country that used metric, and they'll say, oh, that's hot or cold. Anybody in here just knows that? So is this hot or cold? Cold? Moderate. Do you need a jacket? A winter coat? Probably not, right? So you know what it is too? Kind of moderate. So if you convert this, you convert degrees C, multiply by 9/5 and add 32, I think is the way you do it. But you get 59.29 degrees F. But if you were given a homework problem and they said, okay, air at standard temperature is at 59 degrees F, and you started to plug into that formula, it's not going to work. And if you carry your units along, you'll immediately know that because you'll have degrees F or degrees C, and you really need degrees K. So just keep that in mind when we're using this. Okay, so you guys go ahead and plug this in real quick. I'll let you work it. Hopefully you have a calculator. You can pull up your cell phone, turn it sideways so it's easier to use the calculator. Or use the calculator on the PC there. And I do this often. I'll have you guys calculate stuff, and then people will give me answers. Please, please do not be embarrassed if you don't get the right answer the first time. It happens all the time. Sometimes when I work problems, I will miss something and get the wrong answer. And so please be willing to volunteer. And if you get it wrong, next time you'll probably get it right. Don't worry about it. Nobody's going to make fun of you because we're all working through this together. Anybody willing to venture an answer? What do you got?
1.225.
Those match? The other people match? So how did you guys all got that, right? So you have to work the units, right, to get that. So how do the units work out? We've got rho is equal to, we got the number up here, that's newtons per meter squared, right? Yeah, so that's the pressure. So solving for rho, pressure divided by R, which has units of joules per kilogram degree K, and then we've got the temperature in degrees K. And I encourage you to put the units in when you calculate it, because that will help you check. So the degrees K cancel out, and you go, okay, we're good there. Right, and then a joule, we have to remember a joule is a Newton meter because it's force times distance to give us work. And so the newtons cancel out. So those cancel, newtons cancel out. Kilograms goes up on top. This meter and this meter stay on the bottom, so that's how we get the units. Wow, and somebody that teaches in here regularly told me that black works best. I agree, huh? Can you even see the green? All right, another property of the air that we need when we talk about an airplane moving through the air is what's the velocity of the air. So let's define that. So let's draw a wing up here again. And I'm going to draw the air flowing around the wing like this. And these are what we refer to as streamlines. And the idea is that if you have a little tiny fluid element here, so there's our box, if you trace the motion of that, that forms a streamline. So it's the path of a fluid element. And that's how we define velocity of air. You can't define the velocity of each individual molecule because they all have kinetic energy and they're all wiggling around. But in general, if you take enough of them into a fluid element, you can talk about a velocity that has magnitude and direction. So the velocity at a point B is the velocity of an infinitesimal fluid element following the flow. And your book, I didn't get this copied, but I think maybe I can hold it up to the camera, or you guys can look in your book. They show some really cool pictures of streamlines. Yeah, let me pin this real quick. So now if you look at the screen, even though it's going to be backwards, these are smoke trails. So they inject smoke into a flow over a wing. And it really does follow these streamlines. The smoke particles stay together in the fluid, and you get nice flow like that. Or you can do this. They've done this in the beach wind tunnel here. If I can get it to show. They put colored oil. That's not going to focus, is it? They put colored oil on the surface of a wing in a wind tunnel, and then it streaks behind and follows the streamlines as well. All right, so that's velocity. A streamline is the path of a fluid element. And then, as we talked about a little earlier, we're going to talk about forces on the airfoil or on the wing. Pressure is one of them, and that's normal. Not normal as in normal versus abnormal. It means it's perpendicular. And then there's what's called shear stress, tau. So this is parallel and this is perpendicular. So those are also properties of the fluid. The velocity is, and then the pressure, property of the fluid, and then the molecules bumping into the surface roughness on the airfoil, which creates drag, and another force that's sideways. All right, so your book then talks about the anatomy of an airplane. I think it's to break up talking about all this fluid flow. So I'm going to drag this over to the screen. There we go. So this is talking about the basic components of an airplane. For most of you, this is going to be like, well, yeah, I know that already. But this arrow here, pointing to this piece of the airplane, and this piece, what's that called? Somebody shout it out. What's it called? This thing that sticks out to the left and right. It's a wing, right? Okay. Thank you for being brave. What's this thing that sticks up? Vertical tail, and then there's a control surface we'll talk about in a minute called a rudder. That's the vertical tail, and then what's this other wing-looking thing in the back? It's the horizontal tail, and then this is the engine, right? And then this is pointing to this thing that's real long and connects the wing and the horizontal and vertical tail. And what's that called? Fuselage, right? So why are all these things here? The wing is here to produce lift. If there were no gravity or somebody invented anti-gravity, then we wouldn't need a wing. So that's your challenge. Before you're 30, one of you guys needs to invent anti-gravity. Why is the horizontal tail here? To do what? Well, it's control with the elevator, but it also provides stability in pitch. It keeps the airplane from pitching up and down. And we'll talk a lot more about that. How about the vertical tail? Yeah, it controls yaw and provides yaw stability. Why is the fuselage there? I think I already said it connects the different pieces together. It also is a place for cargo and fuel and people. All right, so these pieces, the vertical tail, the horizontal tail, the wing, are different than what we call control surfaces. So on the vertical tail is a flap that can deflect back and forth, and that's called the rudder. And it's used to control yaw, which is different than yaw stability. The rudder provides a resistance to yawing, whereas the rudder causes the airplane to yaw. Horizontal tail provides a resistance to pitching up and down. Elevator controls that pitch. And then flaps provide extra lift. We'll talk about that more later. And then ailerons are control surface that roll the airplane or bank the airplane. You'll get into the structures of an airplane more in later classes, but occasionally we'll talk about it in this class. This is the structure. Let's see, it's a Boeing B-17. And you can see why it takes so long to build an airplane, because there's so many pieces and parts that go into it. Pieces to define the shape of the wing, the shape of the fuselage, the shape of the tail, and the surfaces like that. Let's see, there's some odds and ends we need to talk about. Throughout the class, we'll refer to some tables, and they're tables about airfoils, and they'll be called NACA airfoils. And you might say, well, what the heck does that stand for? And then we all hear about this. NASA. Do we know what that stands for? It's the National Aeronautics and Space Administration. So then you look at NACA and you go, okay, that must be National Aeronautics and what the heck is C? Well, this is still national, and this is Advisory Committee on Aeronautics. And this came before NASA because there was no space. Well, space was there, we just didn't deal with it. So before NASA, there was NACA, and it was a committee formed at the national level to create tables and data about flight. So when did we change from NACA to NASA? What was the event? Anybody have an idea? The what? Right after Sputnik. The Russians launched Sputnik, and suddenly space was important. And so this was formed. By the way, you know the Russians have a COVID-19 vaccine, right? What's it called? Sputnik 5. Because they're going to beat the rest of the world to the race to get a vaccine. Which is not a bad thing. We just obviously need to make sure that the vaccines that we're going to actually use are helpful. All right, I think we're probably close to out of time. Let me look. I guess I can look on the computer. Yeah, we got a few minutes left. Questions on the homework or what is expected from you guys between now and Friday and on Friday? We're all good? Anybody have any major concerns about the semester? Other than let's all stay healthy, right? And stay in class and be safe. I think I still have this in here, yeah. This was just an interesting article that was in the Sunflower a while back. Do you guys remember Fairmount Towers? Right, it used to be the dorms. So something was thrown out of a window, a plastic bottle was thrown out, and it kind of exploded, but not really. And it turned out he mixed Drano and aluminum foil inside a 2-liter bottle and threw it out. So why would he do that? I actually did this as a kid, not threw it out the window, but if you mix Drano and aluminum foil and water in a bottle, it generates hydrogen gas. And you can put a balloon on the top of the bottle. You have to use a glass bottle because it gets really hot. You can fill the balloon up tight, often it's lighter than air, and you can let it go. It turns out it also contains hydrogen and oxygen. So if you torch it off, it has a perfect stoichiometric mixture, and it will explode in this really cool orange flame that's not really hot. So I'm not recommending that you do that. It's just a fun thing that I think they were trying to do, and it probably got too hot on them, and they threw it out the window. So that's the interesting story to end the day today. All right, I'll see you guys on Friday. Remember, we're over in Wallace Hall. In that room, you guys have classes in there now already? There's a whole bunch of seats with red X's on them, just like everywhere in the world. So don't sit in those, but there's enough space in there for our class. All right, see you on Friday.